Welcome to this video in which we will introduce the Z-transform. The Fourier transform for discrete-time signals and systems, abbreviated by FTD, is a complex function of the angular frequency theta. It provides a frequency domain representation of discrete-time signals and LTI systems. Moreover, because of the convergence conditions, in many cases the FTD of a sequence may not exist, and as a result, it is not possible to make use of such frequency domain characterizations in such cases. A generalization of the FTD leads to the Z-transform, abbreviated as ZT, which is a function of the complex variable Z. It can exist for many sequences for which the FTD does not exist. Also, the use of Z-transform techniques permits simple algebraic manipulations. Consequently, the Z-transform has become an important tool in the analysis and design of digital filters, and it can be viewed as the discrete-time counterpart of the Laplace transform for continuous time signals and systems. In the previous video, we've seen that the FTD of a sequence xn is defined as the given equation. However, in order for this series to converge, it's necessary that the sequence xn be absolute summable. Unfortunately, many of the signals that we would like to consider are not absolute summable and, therefore, do not have an FTD. An example is the sequence x1n is a to the power n un, in which un is the unit step function and from which the parameter a is larger or equal than 1. For example, the sequence 2 to the power n un is not absolute summable, and thus the FTD does not exist. The Z-transform is a generalization of the FTD that allows one to deal with such not absolute summable sequences, and is defined as in the given equation, in which Z is a complex function. When comparing this equation with FTD, it follows that we can obtain the FTD from the Z-transform by replacing the complex variable Z by e to the power j theta. In other words, the FTD can be viewed as the evaluation of the Z-transform on the unit circle Z is e to the power j theta. As such, the Z-transform is a generalization of the FTD. Now let's first evaluate some examples. The Z-transform of a delta function, xn is delta n, is equal to 1. And the Z-transform of a shifted delta function, xn is delta n minus 1, is equal to z to the power minus 1. In other words, when a system consists of one delay, such a delay can be represented in the z-domain by z to the power minus 1. In general, when xn is delta n minus p, its Z-transform is z to the power minus p. As a result, a causal sequence will result in a Z-transform represented by a polynomial of z, from which the powers are smaller or equal than 0. On the other hand, the Z-transform of a non-causal sequence results in a polynomial of z, from which the powers are larger than 0. An example of a causal sequence which results in a polynomial of z with powers smaller or equal than 0 is the following sequence xn, consisting of a sum of 11 delta pulses delta n until delta n minus 10. The Z-transform xz of this function is the given finite sum of negative powers of z, which can be written as a quotient of the two given polynomials. By multiplying both numerator and denominator with z to the power 11, the 11th order polynomial of the numerator can be written as a product of 11 first order polynomials, from which the first term, for k is 0, writes as z minus 1. Because of the fact that the denominator also contains a term z minus 1, the Z-transform writes as a numerator, which is a product of 10 first-order polynomials, and a denominator which is equal to z to the power 10. A three-dimensional plot of this function in the complex z domain is given in the figure. The figure represents the 20 log of xz. From the denominator z to the power 10, it is clear that for z is 0, the function becomes infinite. This tenfold root of the denominator is referred to the tenfold pole of xz. On the other hand, the roots of the numerator, referred to as the zeros, are given by 10 equally distributed values of z on the unit circle. Z is e to the power minus j 2 pi divided by 11 k, with k is ranging from 1 until k is 10. These 10 poles at z is 0 and 10 zeros on the unit circle can be represented by a top view figure of the three-dimensional plot. Finally, as mentioned before, by evaluating the z transform on the unit circle, we obtain the FTD result as depicted in the lower right plot. More specifically, evaluating xz at points around the unit circle, beginning at z is 1, which corresponds to theta is 0, through z is j, which corresponds to theta is pi over 2, to z is 1, which corresponds to theta is pi, we obtain values of the FTD x e to the power j theta for theta in the range from theta is 0 until theta is pi. By going the other way around on the unit circle, we obtain the FTD x e to the power j theta for theta in the range from theta is 0 until theta is minus pi. As introduced before, the z transform is defined by the given equation, in which z is a complex variable. The values of z, for which the sum converges, define a region in the z-plane referred to as the region of convergence, abbreviated as ROC. In the sequel, we will show that this region of convergence of the z-transform is an important concept for a variety of reasons. With z is r e to the power j theta, the z-transform can be viewed as the FTD of an exponentially weighted sequence xn r to the power minus n. From this expression, it follows that the region of convergence is determined by the range of values of r for which the given summation is limited. As an example of the region of convergence, we evaluate the z-transform of the right-sided sequence x1n, which results in the given expression for x1z as an infinite summation. If the absolute value of the argument of this summation is smaller than 1, it converges to 1 divided by 1 minus the argument a z to the power minus 1. From this it follows that the region of convergence of x1z is described by all values of the complex variable z outside a circle with radius a. As mentioned before, the FTD can be viewed as the evaluation of the z-transform on the unit circle z is e to the power j theta. In other words, the FTD of the sequence x1n only exists in case the unit circle is inside the region of convergence, which implies that the absolute value of the parameter a has to be smaller than 1. For example, the FTD of the converging sequence x1n is 1/2 to the power n un exists, while the FTD of the diverging sequence x1n is 2 to the power n un does not exist. This table indicates the region of convergence of a right-sided convergence and divergent sequence by shading the appropriate region of the z-plane. In the following, we will show that without knowledge of the region of convergence, there is no unique relationship between a sequence xn and its z-transform xz. As an example, we use the following left-sided sequence x2n, from which the z-transform is given by the given summation x2z. By substituting the variable minus n with p and taking the summation from p is 0, we can replace the summation by 1 divided by 1 minus the argument of the summation, if the absolute value of the argument is smaller than 1. This last expression can be rewritten, from which the region of convergence is given by all values of the complex variable z inside a circle with radius a. From this example, it follows that although the sequences x1n and x2n are different, their z transforms x1z and x2z are the same, but with different regions of convergence. The region of convergence of divergent and convergent left-sided sequences are indicated in the table. From this table it follows that the z transform xz is only uniquely related to the sequence xn if we know the region of convergence. Hence, the z transform must always be specified with its region of convergence. Moreover, the FTD of a sequence can be obtained simply by evaluating the z transform of a sequence on the unit circle, provided that the region of convergence includes the unit circle. From the finite sequence x3n, it simply follows that the region of convergence of a finite sequence includes the entire z-plane except, possibly, z is 0 and z is infinite, as depicted in the table. From the infinite sequence x4n, which consists of a sum of a causal and non-causal infinite sequence, the z transform x4z can be found as an addition of the z transform of the two separate z transforms of each sequence separately. x4z can be rewritten as the given expression, from which it follows that the region of convergence can be described by an analysis, as depicted in the table. From this last example, which is a rational function xz with two poles, one at z is a with an absolute value a smaller than 1, and the other z is b with an absolute value of b larger than 1, it can be shown that in this case the three different regions of convergence are related to three different sequences xn. In case the region of convergence is described by the region outside a circle with radius b, the first sequence xn is denoted by the equation in the first row of the table. Thus, for this region of convergence, the sequence xn is a causal and divergent sequence of samples from which the FTD does not exist. On the other hand, if the region of convergence is the analysis which is described by the inner circle with radius a and outer circle with radius b, the resulting second sequence xn is given in the second row of the table, which is a non-causal convergent sequence from which the FTD exists. Finally, when the region of convergence is described by the region inside a circle with radius a, the resulting third sequence is given in the third row of the table, which is a non-causal diverging sequence from which the FTD does not exist. In general, it can be shown that a rational function xz, which has poles with r distinct magnitudes, has r plus 1 distinct regions of convergence, and thus such a rational function xz can be related to r plus 1 distinct sequences xn. This ends this video in which we explained the concept of the Z transform. It is important to note that the time domain representation is the domain where the signals are generated and processed, and the implementation of the filters takes place. On the other hand, the frequency domain has physical significance when analyzing frequencies, while the Z domain exists primarily for its convenience in mathematical analysis and synthesis. In a follow-up video we will show the main properties of the Z transform. Thank you for your attention.